To give us a good handle on how we can move from one dimension to two dimensions and moving between that linear motion just in one dimension to where we're going to head in our two-dimensional problems, this problem is a really good way to look at that aspect. So we have a clock, and initially the minute hand is on the 11. And after 55 minutes, the minute hand is on the 10. If our clock's working properly, that's exactly what we want it to be. And we know that the length of our minute hand is going to be 0.178 meters. So we've got that R, and we're going to need to figure out the angle, because really that minute hand is traveling in a polar coordinate system. It's traveling with circular motion. But because where we are and where we're headed, we want to look at this in terms of our X and Y components. And this gives us a nice link between how circular motion is going to help us out down the road, and how we're going to be able to do and break apart the X and Y components, because remember, we're talking that X and Y are going to be independent type motions. And so what we want to do is we want to find that average velocity of the tip of the minute hand. Because I want to think about it. There's a really good video out there that talks about why, if you have a little kid, you want to put the little kid close to the center of the merry-go-round versus traveling on the outside of the merry-go-round. Because even though we're traveling with the same constant circular motion, you know, the merry-go-round is not changing how fast it's going around in a circle. The distance that you travel on the outside of the circle is significantly different than if you're traveling on a circle that's closer to the middle. Think about ice skaters, think about horses doing, you know, the turns. So you know that if you're on the outside, if you're an outside on the ice skater, you're gonna have to skate a lot faster to keep up with the person that's on the middle, even though that circle, everybody in that circle is traveling at the same angular speed. So we're looking at it, but right now we want to look at the tip of this minute hand. So we really want to look at that tip. So the first thing we need to do is we got to figure out these angles, right? We got to figure out those angles. So what we want to do is we want to look at our position vectors. So we've got our position vector 1. This is where we're starting at. Now the vector, or the minute hand is going to go around the clock this way, but we're going to end up over here, and this is our position vector 2. So we can look at our position vector and we can write it out. Remember, we can look at, this is we can look at the cosine of this angle, or we could do it with the complementary angle. Remember, there's a lot of times there's more than one way to do this problem. And we have to make sure we're keeping track of our coordinate system. But because we know a few things, we're going to do it with the alpha and the beta. So we need to know the angles. So we got to make an interpretation here. So we're going to take 360 degrees divided by 12, because hopefully our clock is separated out in nice 12 increments there, and it's 30 degrees between each of the numbers on our clock. So if 3 is at 0, we know 12 is at 90, and 11 is at 120 degrees, and 10 is at 150 degrees. So that's going to be our alpha and our beta, just like what we had with our diagram, our alpha and our beta. So now we can go ahead and populate and figure out what our vectors are. So we know that the radius of the length of the minute hand is 0.178 meters. And we know it had the cosine of 120 degrees, the sine of 120 degrees. And now when we actually do those little calculations, we get a negative in the x direction, which is what we certainly hope so, because this is in that coordinate system. The x is going to be negative up here and y is going to be positive. So this gives us a good chance to check our numbers, that we've got the right signs. And then we can do the other thing that we know we're going to have to do is our average velocity is going to be our change in position vector with respect to time. And we know that we've gotten 35 minutes or 55 minutes, and we need that to be in seconds. So we're going to have to convert that into seconds. So we've done that. And now I can do the difference between my R2 minus my R1. And so here's my R2 vector. All I've done is translated that down here. Here's my R1 vector. We got that. And now we get our other vector that we have. And so now I can do the calculations to get our velocity average. We can plug in our change in time across both of those, and we can ultimately find the magnitude in meters per second. So we can utilize our two coordinate systems, we can break apart the motion, and we can still find the relative velocity fairly quickly by looking at it this way.